Hello everyone, good evening. My name is Preeti and today I'm going to present on the topic You May Not Need Attention. It's a paper by the authors Ophir Press, Noah Smith and from the Allen Institute for Artificial Intelligence in the University of Washington. This paper was published just 6 months back in the month of October in 2018. And let's see. So the abstract of the paper is that we are trying to propose a new recurrent neural network translation model for language modeling, and this model is basically like more eager model, like it translates as soon as it understands that what the next word would be. It also performs at par with the attention-based models that have been proposed earlier in 2014. The architecture of the model is such that it doesn't have a separate encoder-decoder style architecture as in attention-based models. So it's a different kind of architecture than the usual attention-based model. So the motivation to learn this kind of model is that it's simple, it's eager, and it is being compared. The results are pretty much good and have been compared with the attention model. So it's a good method when you good approach to go forward if you don't want to use the traditional algorithms for language modeling. Also, it uses less computation when you're doing inference, while inference. Also, the encoder and decoder are modified in such a way that they're combined into a single module, so that it makes the architecture a bit simple. So, I'll start with an example. Here, the tokens in the blue are source tokens, and the tokens in red are target tokens. The sentence that we have is the white dog in English, and we are translating it into Spanish, which is el perro blanco. So we see that while translating, it's a two-layer LSTM model. While translating, in the second instance, that the second pass, it is not able to predict the word white, so it tries to add an epsilon in the place of white and tries to understand that what the word could be. In the third instance, it understands that the word dog could be translated to perro in Spanish. So it translates. And then, when it understands that all the three tokens in English are the white dog, the fourth instance it will translate in Spanish the word white to blanco. So whenever, because it's an eager architecture, whenever it doesn't know what it could predict, it will predict an epsilon value, like epsilon is the padding token, so it will predict that and then it will move forward. So this approach is creates a dynamic memory vector and emits as soon as it sees source tokens. Like it tries to emit the target tokens as soon as it sees the source tokens. So for this model, we would need a lot of pre-processing because while training, we need the source and the target sequences that are there to be of the same length and should have these padded tokens in them, so that while training it understands where the source token is and where the target token is exactly, so that it could predict the actual sentence correctly. So for that pre-processing, where we have S as the source sentence and T as the target sentence, and the size of the source sentence is I and target is J. They use the alignment off-the-shelf alignment model, which is called fast align and is cited in the paper in 2013. There they insert a minimum number of epsilon tokens in the target sequences such that both the sentences, source and target, would be of the same order and would help the eager translation model to predict the words correctly. So in the paper, as you see, if the position of the words is different, then it would try to insert epsilons in such a way that the prediction it would help the model to predict better. In the paper, they also mentioned the proportion in which you should add the epsilons. So you cannot randomly add epsilons wherever you want if it is added unnecessarily or is added at places it's not wanted. So they had mentioned a proportion for each language when we translate from each language. For example, for French to English, it's 23%. That's the average percentage of epsilons that could be added in your target sentences. So it reduces when it comes to English to French. because of the context or the number of words when we translate that particular language. Same with Dutch to English and English to Dutch. So briefly, I would like to explain the off-the-shelf alignment model that they used previously to align their sentences. So they have a source sentence which is of size n, which is called f, and they have a target sentence which is of size m. So for each sentence that they have, the source and target, they try to create an alignment vector which shows them where exactly the target word would be with respect to the source, so that it knows exactly where you will find the source target mapping, like exactly. And it will finally, after seeing all those matrices and vectors, it will understand and it will finally generate a translation which is dependent on the source sentence. And it will understand that, okay, for this sentence, for this source sentence, this could be the target sentence and these are the alignments where it should be positioned. So here, as they see, they try to come up with a probability that it should be close to the diagonal, so that it will help them understand that like where the position of the word should be ideally. That could help them. The probabilities and the hyperparameters for the algorithm help them understand where the position of the alignment should be. So that is the paper. So I have referenced this paper in the references section so that you could dive deeper and understand exactly how they are implemented. So they have taken the whole algorithm and pre-processed the data completely before training. So at the end of this, the output of this model is basically, it gives you source and target sentences which have epsilons in them, and they are of same order and they are aligned. So that's the output.
So just a quick clarification. So if it's actually along the diagonal, then you're almost translating for word. So those languages, whatever they are, they have word for word correspondence. If you get away from the diagonal, those languages are supposedly less, in a sequential way, one-to-one corresponding.
So just about the model, after we get those translations, like we get the source and target sentences of the same length, the model will embed, it will accept each input word and previously the word that it had gotten output as. So in the previous case, the example that we had, so the white dog, so it will, in the second instance where it's translating white, it will take input from the previous word that it emitted, that is L in that case in Spanish, and the word the. So it will use white and L, both the words for their, to represent the next state, like understand or predict the next word. Those words that he's trying to use in the current instance and the previous instance are fed into the LSTM layers. So there are
the previous selected output, where is it, like the previous the time step? Previous time step?
Yes. So the question is, if I understood, the previous word from the previous timestamp, right? The targeted word from the previous. Yeah. So the question is the previous timestamp, the word targeted in the previous timestamp used in the current instance? So yes. So the model will accept the current input word, that is from the source, and the previously output word from the target, and it will create a representation that will be fed into the LSTM layers of the model. So it's a multi-layered LSTM. It has 4 layers, and the vectors are fed into it. Once we get the output of that LSTM, we pass the output to a fully connected layer, and the fully connected layer transforms the representations into the target translation, and you get the actual sentence after the fully connected layer, where we use softmax and embeddings to get the output.
Sorry, how do they initialize their hidden state for the first LSTM layer?
I believe, I could be wrong, but this model essentially does not deviate too much from the LSTM language model that was they used from another paper. So I would just say initialization is probably some kind of random normal, but I have to check that.
Yeah, it's usually either Hay or Xavier initialization. But you're embedding, right? So I guess more towards, I think that it's random. Like you're talking about the layer weights, or you're talking about the embeddings?
When you're feeding starting the layers, you have to feed the initial hidden state to the LSTM.
Yeah, is the question weights? Are you inquiring weights or the embeddings?
Weights.
Weights? Okay, it's probably either He or Xavier initialization. Whatever LSTM is.
Do you mind repeating the answer to quiet, or sorry, louder?
Louder? Yeah, so the question was, what's the weight initialization for the first layer? And the answer, I think it's whatever using standard LSTM. I'm guessing either Hay initialization or Xavier initialization.
So in the model, there are two concepts that they use to keep it aligned as well, to keep the source and targets on the same page. So aligned batching is that because it looks at only the current state and the previous state, the first thing that they keep in mind. The second thing is that they always have the source and the target at the same size. So that, because when they traverse through the entire sequence, they use eager translation. So they have to keep in mind that they are at the appropriate index when passing the entire source and target string. As they are predicting immediately, like they are trying to translate immediately, they need to keep a track of the alignment and the size of the source and target sequences. Second is while decoding. So because this architecture doesn't have encoder, decoder, but typical architecture. So while decoding, they make sure that whatever padding they have done as part of epsilons, once it reaches the highest limit, like the limit that it should have, it sets the probability of epsilons to 0. So it will not pad any more epsilons in the sentences, in the target sentences. And the second thing is that the source padding injection. This is when, for example, in the source sentence, it sees that now you have an end of source token, like you have the end of sentence in the source sentence. So it will understand that now the model needs to insert epsilons in the source. That is because it will give time for the model to predict the target words. Because if it has not predicted it earlier, like if it has not predicted all the tokens earlier, like correctly, if there's one word that's pending, and so it will give time for the model to predict that word by injecting the epsilon in the source sentence. So that's what we're trying to do.
Just for clarification, so if you remember the example, let's say you want to translate from English to what was it, Spanish, was it? And then you have white dog. Let's say your sentence ends with white dog, right? In Spanish is what, perro blanco?
Yep.
So white dog is the last one you've seen dog, but you haven't generated blanco yet. White has come earlier, but you haven't generated it because you want to see what thing it is, and in Spanish it has to come after the dog. So you generate dog. If your tokens end in the source language, then you can't. It's an LSTM. You can't really generate anything else. So you stop without saying white or blanco. So you add those epsilons in the source language so that you give it time to generate actually what it hasn't yet.
This is the example to understand. Yeah, so this is basically how.
So I just want to clarify. When you say aligning, means the source and the target will have the same index.
Sorry, could you speak up a bit? Thanks.
So when
like really loud.
I can repeat the question. So
okay,
he's
sure.
saying when you say align, do they have the same index? No. So the answer is no. So they could be cross-aligned. If you show the alignment graphs.
But should it, like the target word, always be after like the source word?
Given what language you're.
Because if it's eager, so.
Right. So you're talking about
there are ways of guaranteeing that. It's essentially inserting epsilons.
Mm-hmm.
So
Like this, right? Like if the word is earlier and then in the target it's far ahead, what you're saying.
Yeah.
Like it keeps a track of the alignment. The fast align algorithm keeps a track of alignment matrix that helps them understand that if the source word is at this location, then the target would be probably at particular index. So, but this the example A is before the epsilons and E is after, so probably it will help them predict the words once it has time.
So the alignment takes place disjoint of the LSTM.
Yeah, the alignment.
So I just want, so for the epsilon, one of the purpose is to make the source language and the target language, they have the equal length. So that's one purpose. And the other one, I think whether, I don't know whether I'm getting it correctly, but so say for example, in the figure, it's trying to have a eager feasible. So it's just like inserting the epsilon to pair the words. Is that correct?
Yeah. So I repeat the question.
Because I was like confused. Like because in the B, so from A, the source language and the target language, they have the same length already. So what's the purpose to add an epsilon, and in what kind of positions?
When it tries to predict the word, right, if it doesn't know what the word could be, it will put an epsilon there. So for example, in this example, when it sees the, it knows the translation would be L, so it translates to L. But when in case of white, it doesn't know what could be the word that it could translate, so it emits epsilon in that place. In the third instance, it sees dog and it knows that pero is the translation of dog. So it translates that. After the fourth instance, when it sees there's end of sentence, it understands that the sentence is the white dog, and the and dog are already translated, so it translates white. So if it doesn't know what it could predict, then it will put epsilon in that place. And
maybe it's less doesn't know what to predict, and more is it the time to output that token?
Yeah. Probably like it would take that much time or number of iterations to understand that sentence. So it would take that time and put epsilon in that.
Yeah. So in Spanish, you can't say blanco pero. It's pero blanco. So you have to generate pero first. So it has to wait for dog to occur, translate that, then go with the modifier.
And to your question, I don't think source and target are usually they're necessary of the same language. They're two different languages.
So it's not necessary to have
No,
equal.
I don't
Okay.
think so.
Okay.
For probably different languages, the number of words vary. And so I think it would be of different languages.
Yeah, but English and French are close. Same with other Roman languages. They're close, but they're not necessarily the same.
I'm just asking for clarification. So my understanding is that these unknown ones are used in order to provide some space for doing the swapping if necessary, and that sort of functions for the language, right? For example, if you have this pair and if you want to switch the positions when you want to do a word-by-word translation, so you put this unknown words in order to make it possible by the probability that you change their position.
I don't think you could change the position, I think.
No, for example, the white flag, we say the pro blanco, so you have to change the translation position from the real ones.
Could you repeat the question?
And just mainly like clarification, whether my understanding is right or wrong. I'm saying that the intuition behind using this epsilon is that it will provide us with some space to do swapping in the sequences, right? And I was wondering how many of these, the padding, how many of these are we allowed to put in? How is that determined?
They have a percentage for every language. They have defined an average percentage that will be the maximum limit to pad those epsilons. That for each language. But in the algorithm they define, like I'll show you a code snippet where they understand that where we should put an epsilon, and there should not be unnecessary.
So this is mainly based on the semantic relationship between the two languages, right?
Yes, yes.
I think it's a hyperparameter and it's preset how many, like there is a max. decoder is.
Yeah, so the preprocessing.
So you had a question.
Okay, I remember. I think my question is when you actually have that architecture to predict, right? So, so because like when you mentioned the two languages can actually have variational length. So for say that one word could actually predict two words, right? And then both the input word and both the output word are all represented by vectors, right? So in this case, your input is one vector, but then your output two vectors. Is that the case?
Like the whole source sentence would be one vector. Like
Oh, like
the whole,
concatenate.
yeah,
Like
so,
really long.
Yeah, so really long sentences in that case. So each instance, so probably if in English there are just 3 words and in French there could be 4, then it would be a vector of 3 and 4 size, and then they would make the epsilons would help them make create vectors of the same size.
Where to cut the really huge long vectors? Do you know?
So the vectors won't multiply. You still have only one vector, right? But what happens is that they put epsilons. I think both in source and target. Is that correct?
To make it
So
same size.
so for that epsilon, now you receive the vector for the epsilon, and you go output something, right? Given what you have output previously, right? So you have information of the previous word. So it's not like you need to produce 2 vectors now. Yeah. So it's only one vector at a time.
I feel there's a, I guess, misunderstanding because all we were talking about before were doing the pre-processing step. The language model itself is really just an LSTM language model. So it is like what Ehsan said, usually work on one vector at a time, and you roll that over like through time. So I think usually it's still one vector at a time.
Yeah, it'll become clearer as you go on.
So I'll show so this is the pre-processing step where we try to add the epsilons. So we move through all the lines that we have. We divide it into source and targets, split them there, and calculate the length of source and targets. There is a cost variable that helps us keep a track of how many epsilons are being added. So in the beginning, for the target, we add 3 epsilons to give it that time to predict the first word. In this, I is the number of tokens in source and j is the number of tokens in target. So once we go we compare the indexes where they are, right? So in target we are already three places ahead because we inserted 3 epsilons in the target. So we are on the on the 4th token in the target, but we are still on the 1st token in the source. So your the source, the source has to be always less than that of target. Like you have to be you have to be behind in the source and target so that it could predict the correct word. So, but when I is greater than j, like it moves far ahead than j, like your source is far ahead than your target, then you need to calculate a difference. So if, for example, you are at the word white and you're still at the word L in Spanish. So ideally you're at probably 3, your epsilons that you appended in target plus 2. So you are at 5 and at the 1st token in the target. So 5 minus 1 becomes 4. So your difference is ideally of the index is ideally 4, which is greater than the number of epsilons you inserted, which was 3 in this case, right? The cost becomes 3. So when it sees that you are far ahead in the source and you're way behind in the target, it understands that it should calculate a local cost. That will help the program understand that you are way ahead in your source and your target is behind. When it calculates the local cost, it would insert an epsilon in that place, and the index is calculated by j plus cost. J is where your target, like where you are at the target. In this case 1 plus the cost, that is 3 epsilons that you had in your target. So 3 plus 1 makes it 4. So in the target, it will insert at the second position, like, and increase the cost to 1. Like, it'll increment the cost variable by 1, so that you understand that in the target you have inserted 1 epsilon there. I'll try to make it a little clear example that I had. So if we are here at white and it has inserted 3 epsilons in the beginning in target, and we are at the first instance there in the target, so the fifth, so it is 3 plus 2, which is 5 in the target and 1 in the source. Sorry, 3 plus 2 in the source and 1 in the target, so I becomes greater than j, and it enters the loop to calculate the difference between the indexes. And once it calculates the difference between the indexes, it understands that the cost is less than the difference between the indexes. So it calculates a local cost, which says that it should insert an epsilon in the target. That helps it understand that it should insert an epsilon in the target because it's way ahead in the source. And once it inserts the epsilon and it goes to the next value, the difference becomes because cost becomes 4, like it increments cost. When you go to the next token, the difference is same as the cost. Like the difference is also 6 minus 2, which is 4, and even the cost is 4. So it doesn't again calculate the local cost and doesn't insert the epsilon. So
I mean, on a high level, it's a way to control how many epsilons you're putting in. And the cost goes up, that means like now you have more tolerance of how far things are. That means you're putting less epsilons in. But you can look at it. It takes a little bit to figure that out. It's an iterative sort of algorithm. You can look at it on your own, I think.
Yeah. So once it inserts all the cost and it knows that where it has inserted the epsilon and values of the cost, how many epsilon it has inserted, it will calculate the length of the source and the target. And because as mentioned, there could be different number of words in each language. To keep it same, it has to insert extra epsilons in the target as well as source. So if the source length becomes greater than the target one, it will insert in the target. Same goes with if the target length becomes greater, then it will insert in the source, so that it could keep both the sentences of the same length. So this actually, all this adding of epsilons is a pre-processing step. This should be done before we do our trainings.
This is the pre-processing.
Yeah, adding the epsilons, because in the training we need both the vectors to be of the same size, and the epsilons have to be added so that we understand where the index of the word is. Yeah.
Look at the previous screen. I just want to ask about the target split. Yeah? With single line. The target split line. The target itself is like literally translated word from the source. Right?
Yeah. So it is the final translation that you get from the word, from the sentence. Yeah. So these are the validation and the training. They separated them. A is all the sentences that they have, and valid is just a value that they have defined as a global variable which has some finite value, 3000 in this case, to just keep it, just divide the sentences into different sets. So in this algorithm they have implemented two dropouts. One is for the embedded dropout, and the second is the log dropout. The log dropout is ideally applied at the beginning and end of each pass, like while they do in the layers, like in between, while looping through the layers in the LSTM. Here they have set a value of the dropout as 0.5, but for each x that they receive, they create a three-dimensional vector of size 3, and then probably apply Bernoulli function to it and compute the value of 1 minus dropout. In this case would be 0.5, because dropout is already predefined as 0.5. This mask that they create is just created once at the beginning of the pass, and is locked at that point of time, and is the same dropout is being, like the same mask is being used throughout all the passes. That's why they've named it locked dropout. The mask is calculated by the same value, like m, and is divided by 1 minus dropout, and they return the value of the mask that is calculated into the x value that they get in the function.
Why was this locked dropout made in the first place?
So the question is, why was the locked dropout used? Probably. So in general scenarios, I think in RNNs it's difficult to maintain the long-term dependencies. Probably it's difficult to apply dropouts to language when we're doing language modeling. So usual dropouts is that they have they calculate the dropout every time, like a new dropout every time. But in this case, they have just calculated it once, and they use the same mask every time, like in every pass. But like why they have selected this is, I'm not quite sure on that.
We can have a discussion. So I think we have slides in the picture in the appendix to talk about this. I just want to point out that this just is standard dropout. It's just that it's locked in the sense that every time you apply it, it's not reinitialized. I guess that's the whole point of this.
So it's applied to the whole input?
To the entire time
to everywhere. Actually, to the beginning. So when data comes into
every batch that is entered to the algorithm process.
Yeah, every batch at the beginning, and also among, because you have 4 LSTM layers, right? I think in between the layers as well,
yeah.
And then at the output.
I understand, but the thing is that we have already added a lot of noise by putting some places with these unknowns, right? And then we are maybe also by these dropouts we are using some kind. We are deleting the real ones, that the real sources that we somehow made this unknowns unambiguous. So how we are sure that this dropout will actually help? I know it would help that by dropping, by somehow deleting the unknown ones as well, but it may also delete the references to the unknowns. So
Probably that's why they might have not calculated the dropout again and again. And
they wanted to learn that, okay, what was the pattern of dropout, right?
So I have a question before answering that. So is this the locked dropout? Is it between the layers, or is it also between the time steps?
I think both. No timestamps.
Not the time steps.
between the layers,
Between the layers.
like twice, like before the pass and after, like at the end.
Okay, so when you say locked,
Yeah.
is it locked across layers? So it's the same thing across all the layers?
Yes, that is
I would
what
say
we
so.
understand.
I would
Yes.
say that based on code.
Because it's calculated just once at the beginning. Is what
Because there's a detail in there. You see the, sorry, which line? Should I put in the,
Sorry?
okay. I should have put in a line number. Okay, so there's, do you see the Bernoulli over there? So there's an underscore.
Yeah.
That actually means like in place.
Yeah.
I think that means that, wait, is that relevant? Like every time it's not reinitialized.
So that just means that you're not keeping it, right? You're throwing out the previous value.
Sorry, it's a different thing.
Yeah. But trying to say, so I think it's with regard to how we'll get to it in more detail, perhaps in discussions. I do want to let her finish the intro part, but basically for the dropouts in the normal case, you have one dropout per layer, and the probabilities would change such that your neurons don't get too over-dependent on each other, right? So they don't compute the correlation of how things like they don't collaborate, and therefore they learn and they become more robust. I think with a few layers of LSTM, at least my intuition with the time steps, let's say it is time steps, it's not. It's gonna, if you have a different sort of probabilities per what neurons are getting rid of through time steps, you're not going to learn. Like it's going to be very hard to learn. So you would lock it down. For this one, if it's only just between the layers, let's get back to that under discussion. I don't have a clear.
Yeah, we can do that. We have a diagram. Sure.
Yeah. So there's a comparison between what specifications were used for the reference model, the attention one, and the current model that they used with the eager architecture. So they had 4 LSTM layers in the current model with embedding size is 500. They had used regularization as well as the batch size for training is 200. They used stochastic gradient descent with a learning rate of 20, and probably they checked the validations. There's validation set after 6,500 steps, whereas here they are checking after 10,000 steps. So there have been different approaches in both the models, and still they have been able to get good results out of this. So the experiments, now in this we could understand that they are evaluating based on the BLEU score, which is the bilingual evaluation score to assess the language models. Also, we could understand that the eager model takes longer to run. It took about 38 hours to run, whereas the attention-based model took only 13 hours. So we actually tried to contact the authors to understand and to get some insights why some things were different from what we expected, and we have some answers from the authors, so we discussed that. The results are like this on the right.
Let's have a break and we'll do the results after.
Okay, sure. Yeah.
Thank you.
So as we see the results, they have displayed the results for French to English and Dutch to English, where we see that the eager model performs better on longer sequences, like when the source sentence size is probably greater than 60, it performs a little bit better. But for smaller sentences, the attention-based model, the reference model would perform a little bit better than the other one. So, but they still say that, it's just, if you see French to English and English to French, they say that it's just 0.8% worse. So they still think that it works better. And for the Dutch to English and English to Dutch tasks, it is probably 4.8% worse. That is what they say, that it's still close to the attention-based model. So,
just want to add one thing. The reference model is essentially the original attention model.
Yes.
So the whole point of this is you may not need attention because the results are comparable here.
So that's the references. First is for the off-the-shelf alignment, the fast align paper. The second is the GitHub repo for attention. And the third is all the regularization and optimization paper has in-depth understanding of the dropouts, the locked and the embedding dropouts that help it, regularize the model better because it's a recurrent neural network model. So that paper helps us understand those dropouts in detail. Yeah, so discussion points is, so when we spoke to the authors, we got answers to one of the discussion points that we had earlier, so I've just mentioned the answer. So the discussion points are why the difference between English to French and French to English, like vice versa. When we see there are difference in the results and the way the BLU score, the output of the BLU score is. Second is why do we use dropouts inside the LSTM layer, like between the in the timestamp that we have. Next is the author mentioned this, that the eager model would work very well with the transformer XL architecture. Recently we had a presentation on the transformer XL architecture here, so they haven't tried this working combining the eager model with the transformer XL architecture. So they think that it would perform well. And next question is, there's a sequence length that they use, like a hyperparameter that is used. So why do they change the value of the sequence length? Why is it variable? So that is the code that was there in the repo, like the value of DPTT is changing over the time, and then why does it change? And the third and last point was the model is simple and still it takes longer time to train. So the author mentioned that the alignments that they receive from, like they get from the fast align after the fast align algorithm is applied, might not be very perfect. It might insert epsilons at wrong places or probably might be missing. So to deal with all those things plus the translation, that could be the reason that it takes longer to train than the attention-based models. So
I just want to add to another point. I think they mentioned. I think it's also, interesting. They gave, that's the one reason they gave, right? The alignment, because alignment is not perfect.
Yes.
And the other reason they gave is this is just guess speculation because nobody knows the exact answer of why, like if we don't have like more rigorous tests. So the other reason is because if you think of eager translation, it's always, when you're translating, the network always only has partial information as opposed of the sourcing, the source sentence, as opposed to say an encoder decoder model where it goes through input sentence, goes through an encoder, so it has the whole of the sentence before it can start doing the translation of the decoder. So the authors speculate, like they replied to us, they speculate that because there's partial information, so that's why you need to go over more iterations for it to converge. That's why it's like 3 times long. That's another reason in addition to this.
Sorry. Is there any reason why they use the SGB?
SGB?
They could have used the Bahdanau instead. Because the base model they're trying to compare to use SGB.
I'm not sure, but I think it maybe there. One reason is because again, they are just using the established language model, and in that they also replied. They said we are not really altering anything from that language model. We're actually just we use straight their code because that code base may be using SGB, and I think the reason that. Yeah, I'm not sure about why they are not using Atom in the other paper.
Yeah, maybe it was before Atom really caught on.
Maybe.
Because LSTM is also old.
I'm not too familiar with natural language evaluation, but the number of sentences seems kind of small. Is that typical? It's like 1,300 max sentences in a couple days. So the first, like the sentence length and the performance.
Is that the test set? That's a test set, right?
This,
Yeah.
like this
Yeah,
length of
testing.
the.
It seems just kind of small to me. Is that standard?
Because they want this to be comparable with to compare this with the 2015 paper. So everything is like probably a lot of things are by 2015 standard.
I guess an extension to Julia's point is that, so actually, I guess is when you build these type of models, generally you don't need a lot of data to train this model. Is that true? That you can already obtain some kind of accuracy?
So the more the merrier, right? For statistical machine translation, it's ideal to have parallel corpora. So you have such that you have for each sentence you actually have a sentence out there, and sometimes they're hard to attain. I think technically parallel corpora is okay. This is a news article about this title, like this is almost the same article in French. That probably you can train machine translation on, so that's sort of more flexible. Anyhow, but it's not easy to come by, like bilingual text. Sometimes they're limited to legal documents, sometimes newswire. So it's data isn't really always easy to come by. But yes, the more the merrier. You need so it's an LSTM. It's a deep network, so it's definitely preferred to have more.
Did they make any mention of how to handle punctuation, or did they just treat it as another token?
It is a token in the vocabulary. So what did they do with the punctuation? Did they sort of get rid of them? That's the question, right? And the answer is that it's an LSTM. It's part of the vocabulary.
So this is the modern.python function that they have. They use the previous targets that have been predicted plus the hidden input layer out, like the source sentence, like the next token in the source sentence. Once they go into the loop, as they said, we first apply the log dropout here and an embedded dropout. So before we enter into the LSTM loop, they have applied the log dropout. Then they go into the LSTM layer where they compute the output and the new output from the earlier states. They also calculate the hidden layer, the new hidden layer, and append it. So number of layers is 4 ideally. So if the number of layers, like for each layer, they will at the end again they'll calculate the log dropout value and compute the outputs. So it will iterate through. It will iterate through. The loop will iterate through all the layers continuously, and would generate the outputs, and for each layer probably it could, at the end it will calculate the log dropout again. So just a short description of the embedded dropout is that certain words would be favored more than the other words. So if a single word is having a lot of impact on the sentence, it would cause overfitting. So the embedded dropout is designed like they have programmed it in such a way that it will help discard those words and help prevent overfitting, so that whenever some word would like the network would be biased to it, it would get rid of the whole word. So once it is computing, after it computes the outputs, you have the tanh. Is it possible? You have the tanh where you have the combiner. So the combiner is basically a fully connected layer that they have defined in the beginning of the program, and they used it here. So we get an output, like the output of the code would be a matrix like 3 of dimension 3, and the decoder is also a fully connected layer. Like as I said, the fully connected layer would be helpful to decode the translation that they have predicted. So after the LSTM would be the fully connected layer, and then it will give you the outputs after the activation function. So that is why we have combiner and the decoder, which are fully connected layers. Again, we have a log dropout layer, which will help it, which will help the weights to be to be uniform or consistent. So the dropout was calculated once earlier, and it is used continuously. Like the same value is being used throughout the loop, and they return the result and the hidden layer. So this function, the forward function, is written after you initialize. Like there's an initialization function and the forward function and the hidden function, like the 2-3 functions that are part of the model.py program. I think this is the diagram that we were talking about earlier, where you know, when we apply dropouts, it's usually it's usually through layers, like not in between layers. It should be probably through like between the 2 layers, not in between, through time, is I think what he was trying to explain earlier.
Yes, this is, I think this is a diagram that's that is derived retrieved from a paper that there's like 2 layers in the middle. This paper references another paper which represents this paper, I think. And but I think this is a good diagram that it's it kind of explains, helps clarify things. So you can expand in 2 ways. One is like you have 4 layers of LSTM, so stacked on top of each other, and you can expand along the time horizon as well. So when you see dotted line, those areas are empirically permissible areas to apply dropouts, but never across time span. Like, because if you do like dropout across time, then I think information like quickly gets lost. So that's why you see that in the while they loop over the 4 RN layers, so they also apply a log dropout in between. So the log dropout in here basically says every time, because the dotted line in the middle, every time stamp you apply another time. So I think what log dropout essentially is that throughout the application, like as you move along the time horizon, the mask of the dropout is fixed as you move along, if that makes sense. Also, we have the author here in the chat room, so if you want to ask questions.
So in the main .py, they have like divided the training and test set, validation set, etc. So when they build the model, they have the the model class that we first defined earlier. So the RMN model class, and they pass all the values like the embedding and the number of layers and the dropout values that they have. all these values help are like all these values are passed through the earlier function, like the earlier class that we saw. And so by the way, this code is in PyTorch. just remember that.
Okay.
I have told it earlier. But it's good. Okay.
I don't think,
Yeah. Basically, it's usually the functions that are there in the main.py, like the main Python file, so that they are to evaluate or to train. They are basic functions, the usual functions that we have for training, evaluation, etc. So it's ideally implementation of the usual LSTM language model and has nothing different from that. But the main part that has to be understood is the adding epsilon part and the dropouts that they have defined, so that they could keep their long-term dependencies in check and make sure that they don't lose information along the way. So that's the difference between other usual code that they have.
So the author also commented in the YouTube channel that our point was to show that attention may not be as strong as some people think. Attention may not be as crucial as some people think. And that attention can sometimes cause problems on long sequences.
Also, they did mention that for neural machine translation, the test set size is always 3K. You asked the question.
Yeah.
So you made a point earlier, if I may ask. You said that if you go back to the previous slide, no, next, there you go. Did you say dropout exists in between, but it's locked and across time steps? Or did you say that it does not exist across time steps?
It shouldn't, from what I read, it shouldn't exist across time span. It's just that it's always applied in between layers. But because it's RNN, you apply multiple times in between layers as you move along the sequences.
Of course.
So
it is kind of also per time. I mean, it's across layers, yes. But each time step, you're receiving one input. Then you pass it, you get your hidden state, then you pass that hidden state. The moment you're passing that hidden state to the next layer, then you're applying dropout, right?
Yeah, I think it's in the close half.
Yeah, actually, like first is dropout once, and then once you come inside the loop, then there is again dropout.
There's a dropout.
And probably after that, at the end, like after you complete the outputs, then again you have the dropout before the decoder, like before the fully connected layer. So there's one fully connected here, and then the other is the decoder. Gotcha. So before that also we have the log dropout. But the embedded dropout, where we try to discard words that are biased, that is defined earlier, just once when it goes through before it goes through the LSTM. So they have written these two dropouts specifically to make sure that they don't lose the language, like the context of the language.
So there is a question from YouTube. Somebody asked, is it clear how blue is calculated?
So blue is he one of the authors? So that's the question.
No,
okay. So blue is sort of it's a score, but it's not the best score out there, but it's one of the things that we have. So with summarization, machine translation, we don't have the best score. There are still active area of research. Anyhow, it's somehow of an F measure. You can use F measure, precision, or recall between unigram or n-grams between the sequences of two languages. So a simple simplistic way of saying this is that so blue one could be between, for each word that happens in your source language, you want to make sure, in your human-generated translation, you want to have the correspondence sort of with your generated translation. So you want to have sort of that correspondence, and then there's more than that. So it's a combination. If I remember correctly, we can have bigrams and vice versa.
I just want to add that blue mostly come from it's almost, my understanding is almost like a compromise. What's the alternative is to have humans evaluate the quality of the translation every single time. So what's the next best thing is blue. It's definitely not perfect, but you can run it as many times as you want, and very fast. So it's like a heuristic to evaluate translation.
So it is possible that two methods have the same blue score, but the quality is different. That is possible. But it's indicative usually of the quality of the translation.
So embedding has two dropouts, one like the embedded dropout and one goes to the debug block.
Yes, so
Can you repeat the question?
no, so the question was that the embedding dropouts, like that, they are twice, like, are they two, is it repeated twice? So embedding dropout is just once that they calculate for the words that are biased, and then they input that value into the log dropout, like.
And it's fully random, the embedded dropout, or is it because you mentioned something about being more important or less important?
Like the way like they have, I can just check. So the way they have this embedded dropout is that they have embeddings and some words that could be having more weight than the probability of them could be more than the others, and they could they could be impacting their the training. So if that word is impacting and would overfit the model, then I think they would discard that, and that's why probably they have initialized it in the beginning of the network and not afterwards. And then they use the log dropout which they wrote and create the mask in the layers.
I think it is random because I think the whole point is you use dropout, so it is masked. Like if there's some really important word that the model is dependent on, which could be a case of overfitting. So you randomly mask at times, so that the model overall does not rely on the word on that much. This explanation, I think it was found from some paper, right? Why do we need embedded dropout? But that's I guess the best explanation we could find.
So there's the new dropout that they now, like the recent language modeling techniques use the drop connect, which is in the paper, I think the regularization and optimizing LSTM paper, which I referenced. That paper has all the different type of dropouts that could be used for language modeling. So this log dropout is called, I think, variational dropout, and then there's this embedding dropout. So different kinds of dropout that could help control different kind of behaviors in that language modeling. And the most recent, I think, is drop connect, where they try to remove those some connections randomly, which could help prevent overfitting. So there are different variations of it, and the recent researchers have been using different types of them to try to use language modeling. So that's it. So that's it, I think.
Okay.
Yeah.
Are we?
Any other questions?
I just want to give a shout out to Ofer Press, who is one of the authors. He's right now in the chat room answering questions. I just like to thank the author for coming to the chat room, and also for typing a very long answers to our questions.
In a very short time.
Yeah, in a very short time notice. It was my fault. Yes.
Really appreciate it.
So they mentioned that they tokenize the sentences and then segment the words using.
Yes, speak up.
They mentioned that they tokenize the sentences and then segment the words using 32K BPD. Just wanted to know if you know what that is.
The BPTT, the backpropagation.
BPTT?
Yeah.
Oh.
That is the variable
Sorry.
sequence.
Oh, that's the binary pair encoding.
Go ahead.
Can I see the paper also? I think that's the encoding. Yeah. Oh, byte pair encoding. Okay, yeah, you're right. You've written that. Yeah, so there are multiple ways for you to create the vocabulary. The traditional one is treat each word as an item in the vocabulary. Like, punctuation could be an item in the vocabulary. So divide by space. But that over there you lose information, subword information. Right? You have also the number of vocabulary can be really big because you're not really restricting it in any way. Also, specifically for machine translation, when you translate from one language to the other, you run into all these encoding problems, English to Chinese. So that encoding is one of the most useful ones, where you start with each character, so each byte, as an encoding, so that your vocabulary is just like, I think, 256. And then you iteratively go over and look to see what are the most frequent sequences of bytes, right? You find the most frequent sequence of byte, you add it to the dictionary. So now your dictionary size, so 256 is 257. You keep doing that to a certain point. There was a parameter there, I don't remember exactly, but you keep doing that. So now your vocabulary is subword. So now if a new vocabulary comes in that you haven't seen before, you're able to generate not an empty token. I don't know what the hell this token is, but you can actually say, okay, this is this and this. You can actually sort of parse in between the word and guess what it is. So you can still output something and encode and decode it.
Lastly, just to go back into to the paper, I think one of we mentioned you mentioned that in the, at the beginning, but I just want to reiterate one of the advantage of this paper is that when compared to like the 2015 attention model, is probably that it has a lot less memory footprint during inference time. So if you think of like how the attention mechanism works, you have to go through all the in the encoding step, you have to go through each single one of them. They have store all the states in the memory, and for the decoder to retrieve, that's a lot of memory consumption. Whereas this, doesn't matter how long your sentence is, it always uses constant memory consumption. And during training time, it's 3 times longer, but during inference time, the model could be a lot smaller and probably faster. And actually faster because you don't have to go through encoder before you start translating. So that's why it's eager.
So in attention-based models, you usually have the entire encoding, all the time steps of the encoding available at decoding taps. So at each time that you're spitting out a word, you're looking at the entire thing and running this through attention. But here you're just generating something, so that's why at each time step, that's why it's constant. You don't have to go over. So having a bigger sort of input sequence doesn't only it's not just one a cost that doesn't get added just one time, but added every time step that you're decoding in the traditional attention model.
Thank you.
Any other questions? Questions for the authors? Very cool that the author is on the screen.
Yes, this is the first time.
So take advantage of it. No? Okay.
Thank you.
Thank you, Preeti.
Thank you.